Hello and welcome. In today's lesson, we are going to be exploring the idea of energy and how it relates to something called a photon, a little packet of energy that electromagnetic radiation uses to carry energy from one place to another. Before we begin though, let's start with some thought-provoking questions. So, have you ever thought about why does the tar on a road get hot when the sun shines on it? Maybe you've noticed it on a hot summer's day walking that the road gets very warm. Well, the answer lies in energy, right? Energy is being transferred to the tar road from the sunlight. But maybe we need to pose another question. Maybe you've seen some of these digital thermometers around at the shops and wondered, how does a digital thermometer actually work? Once again, the answer lies in energy and being able to read the amount of energy or absorb a certain amount of energy and have something happen. But let's go to our concept map to explore these ideas further. So as part of our discussion on electromagnetic radiation, we have already examined how electromagnetic radiation behaves like a wave, how it acts like a particle. We then went on to unpack how it propagates through space. We talked about how fast it travels. Remember, we said that it travels very quickly at the speed of light. We then explored the fact that it was a spectrum made up of various frequencies. Now we can finally take all of these concepts and link them to this idea of energy and see if we can link any of the features of electromagnetic radiation like frequency to the energy of the electromagnetic radiation. All right, so we're going to be looking into how much energy is propagated by electromagnetic radiation. Before we do that, though, we're going to need some key words to help us understand. Our first key word is quantum. And a quantum is simply a small packet of energy that cannot be divided into a smaller packet. Think of something that literally cannot physically be divided, like, say, an electron. We don't get more or less than one whole electron. Our next key word is one we've used before, energy. And we know that energy is simply the currency by which things change in our universe. Our last word that we need to be familiar with is constant. One that's quite common in mathematics, but also in physics. A constant is simply a variable that always remains with the same value in every equation that it is used in. So now we've got these key words to help us along the way. We now can start to unpack this idea of what a photon actually is. So what is a photon? A photon is simply a quantum of energy. Remember from earlier we said that a quantum is a small, indivisible amount of energy. So when we talk about a photon, we are referring to a quantum of energy, a small packet of energy associated with electromagnetic radiation. But this poses another problem. If it's a packet, does it behave like a particle? Well, this question has come up a few times already in our investigation into electromagnetic radiation. So now we need to unpack this idea further in terms of what a photon is, to see if we can work out whether it is a particle or does it behave more like a wave. So what is a photon? We've already said it's a small quantum of energy, but what's also important to note is it has no mass, all right? So it's not like many particles we've looked at before. It's quite unique in that it has no mass, and it also has no charge. Now, if it has no mass and no charge, how can we truly say that it's a particle? Does it then behave more like a wave? Well, the question's come up again, hasn't it? We need to examine whether a photon has properties of either a particle or a wave to get a clearer picture on the answer. So let's have a look. What else do we know about photons? Well, we can say that we already know that photons are associated with electromagnetic radiation, and this means that they travel at the speed of light. Remember, the speed of light is given this symbol c, this very large number and value, 3 times 10 to the power of 8 meters per second. If you recall from our last lesson, at the moment, we're pretty sure that light is as fast as anything can go. So now we are posed with the question, when can we describe the behavior of a photon as a wave, and when can we describe it as a particle? Now, to further unpack this, we need to really have a look at the properties of waves that we've already examined and the properties of particles we've already examined in the context of what we now know about photons. So we're asking the question, is it like a wave or is it like a particle? Well, photons travel in straight lines, and they are able to diffract through openings. Whoops, accidentally opened the menu there. This is definitely a property of a wave, one of the ones we looked at as the very first properties of waves. And the diffraction through an opening is also a property of a wave. In addition to both of these wave properties, it's also observed that photons can undergo interference, just like, once again, the waves we looked at earlier. Now, these are all properties of waves, but does this guarantee that photons are always waves? Do they maybe have some particle properties? That idea of particles diffracting when passing through an opening is part of a very famous experiment called the double slit experiment. If you're interested in learning more, you should go check it out using some online resources. But for now, let's quickly look at how photons behave like particles. So still working with the question, is it a wave or a particle? But now, much like many particles we are already familiar with, photons are also easily able to be reflected. Oops, open the menu again there. They are easily reflected off of surfaces. And sometimes, when particles have a lot of energy, we know that they are also able to penetrate materials. Now, we need to examine whether photons or how photons are able to do these two things as well. So let's investigate further and see if there's some more information. So which photons are able to be easily reflected? Those photons of radio waves, both AM and FM radio waves, are easily reflected. So are infrared photons, as well as the photons of visible light. But what do these all have in common? What can we say we know about them? What can you remember about these three types of electromagnetic radiation? Do you recall that all of these have the longest wavelength? Do you think there's some relationship here between the reflectiveness and the wavelength? Let's keep looking. Now we need to ask which photons are able to penetrate materials, i.e. which are able to behave more like a particle. The photons of UV radiation, like that produced by the sun, X-rays, like those used by medical doctors to look inside us, and gamma rays, those very dangerous ones that are also used in medicine, are all able to penetrate materials. But again, we ask ourselves, what do they have in common? Do you recall that all of these types of electromagnetic radiation have very high frequencies and that means they deliver a lot of energy per second to whatever they're impacting. Let's look further to see if we can unpack this relationship. Looking at a diagram of the spectrum of light or electromagnetic radiation, we can see that our AM radio signals have frequencies that are relatively low in comparison to the electromagnetic radiation produced by radioactive elements. You can see the frequency is 10 to the power of 5 for AM radio waves and 10 to the power of 20 for those radioactive elements. Similarly, we can see that the wavelength of AM radio waves is very large, but as we move across the spectrum, our radioactive elements have extremely small wavelengths. So is there some kind of relationship? Well, we know quite a bit about these types of electromagnetic radiation in general, and we can see that some types of electromagnetic radiation have high frequencies and low wavelengths, and some have large wavelengths and very low frequencies. So what's the relationship to energy? Let's go further. But before we go further, let's pause for a short ad break. Welcome back from that short ad break. Let's continue our investigation of energy and the photon. So, earlier we looked at how the different frequencies of electromagnetic radiation in the spectrum also have different wavelengths, and we used a little bit of our understanding to start to understand this idea of the energy associated with electromagnetic radiation. Now, as part of that, we need to show, or we want to determine whether there is some mathematical relationship between the frequencies of electromagnetic radiation and this energy that it is transferring. So, we need to have a look a little bit deeper and try and see if there is some kind of relationship between the frequency of electromagnetic radiation and the energy that is transferred by it. So to do that, we need to have a quick reminder of what we already know about the spectrum of electromagnetic radiation. From our work on the spectrum of electromagnetic radiation, we already know that higher frequencies of electromagnetic radiation have smaller wavelengths. Do you remember this from last time, where we looked at electromagnetic radiation with different frequencies and then saw that as the frequency got larger, the wavelength tended to get much smaller? Well, is there more to this? Let's have a look. This is a GIF that we've already had a look at, and in it you can see two electromagnetic waves, or two waves. Number one at the top and number two at the bottom. In number one, we can clearly see that the frequency of the wave is quite a bit higher than the frequency of the lower wave, wave number two. If we watch the numbers, we can see that in the time it takes wave 1 to complete 8 full wavelengths, our wave 2 has only just completed 2.5 wavelengths. So certainly the wavelength of number 2 is quite a bit larger than number 1, and that is because the frequency of wave 1 is higher. Now, we've already seen this relationship between frequency and wavelength, haven't we? But now we want to try and determine if there's some relationship between either of them and the energy of the electromagnetic radiation. So let's lean on past physicists and see what they have to say. So we are still posing the question, what is the relationship between frequency and energy? To begin, we should remind ourselves of what we already know. We are a lot more careful and wary of electromagnetic radiation that has a higher frequency. Think of our X-rays and our gamma rays. They're the ones that you don't want to be exposed to. But remember that they also have smaller wavelengths due to their higher frequencies. The question we can ask ourselves is simply why? And how does this relate to energy? The answer, quite simply, is energy is proportional to the frequency of electromagnetic radiation. This means that as the frequency increases, the energy of electromagnetic radiation increases as well. Had you already realized this? That the more dangerous electromagnetic radiation had to have a higher frequency? Well, other great physicists noticed it as well. And they went to try and find if there was a way to equate the energy to the frequency of the electromagnetic radiation delivering that energy. So let's have a look at what they found. So we've already said that energy is proportional to the frequency of electromagnetic radiation. But importantly, it is not equal. We cannot say that the energy transferred is equal to the frequency. So, how are we going to make them equal? A common problem in physics is trying to find how certain quantities or variables can be said to be equal. To get our answer, we're going to ask Max Planck. Have you heard of Max Planck before? He's a famous physicist from 1899 who did some interesting research on electromagnetic radiation. Let's see what he had to say. Max Planck was able to show in 1899 that the energy and the frequency of electromagnetic radiation was proportional. But he was not satisfied with this discovery. He wanted to be able to calculate the energy for any particular electromagnetic radiation at a certain frequency or wavelength. So what did he do? Well, he did a series of experiments, and through experimentation, he found how to equate the energy and the frequency, i.e., how to get an equation that would give us how frequency and energy are related. To do this, he used a constant. Recall we mentioned the constant earlier. A constant is simply a variable in maths or physics that always has the same value no matter what. This constant is named after him and his research and its impacts on history, and it is called Planck's constant. It's a very small number, and it is given the symbol h. Its magnitude is only 6.63 times 10 to the minus 34 joule seconds as a unit. But, valuably, it gives rise to a new formula for us to use. In this formula, we are able to equate the energy of an electromagnetic wave to its frequency by multiplying the frequency by Planck's constant. This gives us our energy reading in hertz. So, had you heard of Max Planck before we mentioned him in today's lesson? Did you know that he was able to develop such an important formula, one that lets us relate energy to frequency? What does this formula, though, allow us to say about that relationship we started with? What does it allow us to understand about the relationship between energy and frequency? Let's have a look. So from this equation, E is equal to h times F, we can see that the energy is proportional to the frequency. Don't worry about this symbol here. It just means that the two variables are proportional, i.e., as the energy increases, the frequency had to increase at the same time. So we say, for the relationship between frequency and energy, that as the frequency increases, the energy of the electromagnetic radiation also increases. Now, you can see this in I've used a normal algebraic sum to help us understand this. I've replaced our constant h with a constant that's just a numerical value, number 6. If we had a function that said y is equal to 6 times x, we would all be quite comfortable with the idea that as x increases, y's value will also increase. But remember, in our cases, h is always a constant. So now we've seen that there is definitely a mathematical relationship between energy and frequency. But what about the wavelength of the electromagnetic waves we've been talking about as well? Is there a relationship there? Let's have a look. So from our formula, E is equal to hf, we are actually able to replace the value of frequency with c over lambda from our wave equation for electromagnetic waves. And this gives us a new expression for the energy of an electromagnetic wave, where E is equal to Planck's constant h multiplied by the speed of light, all divided by the wavelength of the electromagnetic radiation in meters. And again, we can see that now there is a proportionality. But instead, our proportionality is an inverse one, i.e., as the wavelength of electromagnetic radiation increases, the energy of it decreases. I've used another simple algebraic sum to show you again. If we had a function where y was equal to 6 over x, remember 6 is our placeholder for our constant, just like h is our placeholder for Planck's constant, we can clearly see that as x increases, y's value would decrease. All right, so now we've clearly shown that there is a relationship between energy of electromagnetic radiation and the frequency. We've seen that as the frequency increases, so does the amount of energy transferred. And as the wavelength increases, the amount of energy transferred decreases. But what about that idea of penetration we talked about earlier, when something goes into a material? Let's have a look. When examining the idea of penetration, now that we understand the energy of electromagnetic radiation, we're better equipped to understand why some electromagnetic radiation is able to penetrate materials and why some isn't. And the answer lies in the amount of energy. The greater the energy of the electromagnetic radiation, the greater its ability to penetrate into materials. And when they when high energy electromagnetic radiation penetrates a material, it is able to transfer energy to it. So now we've seen that penetration is also linked to the amount of energy. And this maybe starts to help us understand why we take precautions when working with certain types of electromagnetic radiation. Can you think of some precautions that you take on the daily? Let's have a discussion about it. So when should we be careful? Obviously, we should be careful when electromagnetic radiation outputs a high amount of energy, i.e., when it has a high frequency and a low wavelength. But maybe you also recall that many things like cell phones use electromagnetic radiation to send signals around the world or around the country. So when do we have to be careful? Why do we put on sunscreen when we go outside, but you don't worry about wearing sunscreen when using your cell phone? As we go further, hopefully we'll be able to answer these questions. Welcome back from that short ad break. We're now going to continue our investigation into the relationship between energy and frequency with a few questions to get us thinking. The first one of which will be all about that Max Planck's constant we looked at in the last lesson. So let's return to our concept map and remind ourselves what we've been doing. So, we've already been looking at electromagnetic radiation. We've long since established that it has a particle and wave behavior, and we've examined this behavior in terms of its propagation through space and how electromagnetic radiation is made up of a spectrum of different frequency types of electromagnetic radiation that all travel at the same speed of light through a vacuum. We are now looking at more of the energy aspects of electromagnetic radiation. In our last lesson, we looked at the equation E equals hf, which allows us to equate the frequency and energy of a particular electromagnetic radiation. But now we need to do a little bit more unpacking about this constant. So in our previous lesson, we looked at this new equation E equals h times f that allows us to equate the energy to the frequency of an electromagnetic wave. But how did Max Planck determine that constant? Would we be able to determine it? The answer is resoundingly yes. So let's have a look at how. The question, can we determine the value of Planck's constant h? How are we going to do it? First, we need to collect some data on different types of electromagnetic radiation. I've used colors of light from the visible light spectrum. They're nice and familiar to us. We've all seen red, orange, yellow, green, blue, and violet light as part of the colors of the visible light spectrum. I've included each of their individual frequencies, which have a unit of times 10 to the power of 12 hertz. Remember that this electromagnetic radiation has a very, very high frequency. And then I've used the equation E is equal to h times f to determine the energy in joules times 10 to the minus 19 for each of these different frequencies of electromagnetic radiation. But how are we going to find Planck's constant? Well, like with many things in science, it's valuable for us to put this data on a graph and see if some kind of visual relationship can be seen from the outset. So let's see what happens when we graph this information. So here we can see when we graph the data, I've generated a line graph to show the relationship between the energy and frequency of the different colors of light. You can see that on the y-axis, I have my energy, the dependent variable, and on my x-axis, I have my frequency, the independent variable. And when we graph these values, we can see a very clear straight line passing through all of the points on the graph. So what's the importance of the fact that this line is straight? Well, the first thing it lets us do is lets us find a gradient. So let's do that. So when we calculate the gradient, we use the normal gradient formula where m, the value for the gradient, is given by y2 minus y1, all divided by x2 minus x1. And when we substitute our energy values here at the top of the fraction, and we substitute our frequency values here at the bottom of the fraction, and we get a change for each, the gradient comes out as 6.63 times 10 to the minus 34, and the units are joule seconds. And there we have it, the exact same value that we mentioned earlier for Planck's constant. So you can clearly see that Planck's constant is some value that allows us to equate the energy of an electromagnetic wave to its frequency. But what can we use this information to understand more about? Let's find out. I pose you the quick question. Can we explain why we need to put on sunscreen when we go outside, but we don't need to wear sunscreen when we stand next to a fire? Let's have a look. So the first thing we need to know and understand is that sunlight contains dangerous ultraviolet electromagnetic radiation that has a frequency of 8 times 10 to the power of 14 Hertz, while a fire mainly releases heat in the form of infrared electromagnetic radiation that has a frequency of 3 times 10 to the power of 11. So we can already see that there's a difference between the frequency of electromagnetic radiation produced by the sun's ultraviolet rays and a fire. But can we mathematically show that one produces more energy than another? Let's have a look. To calculate the energy of ultraviolet radiation with a frequency of 8 times 10 to the power of 14 Hertz, we're going to use our energy is equal to H times F equation, where H is 6.63. So to do this, we're going to need to use our calculator and multiply the frequency of 8 times 10 to the power of 14, and we're multiplying it by 6.63 times 10 to the minus 34, hitting equals. We get that the answer is a very small energy value of 5.304 times 10 to the power of 19 joules. So 5.304 times 10 to the power of minus 19 joules. But what about the fire? How much energy is its electromagnetic radiation producing? The fire releases electromagnetic radiation of a frequency of 3 times 10 to the 11 Hertz. And we're going to use the same formula to calculate the answer. So let's bring our calculator back up. This time, however, so let's just clear it quickly. We are using a lower frequency of 3 times 10 to the 11 Hertz multiplied by 6.63 times 10 to the minus 34 for Planck's constant. Hitting equals, we see that our energy value for the infrared radiation is much lower at 1.989 times 10 to the minus 22 joules. So, quite a big difference in the energy, hey? Can we use this then to understand the answer to our question? The photons of UV radiation only had an energy of 5.304 times 10 to the 19 joules. But the infrared radiation was even lower at 1.989 times 10 to the minus 22 joules, an order of magnitude of 1,000 times less. Therefore, we can clearly see that the UV photons have more energy than the infrared photons. Hence, as a result from our earlier discussion, we can say that UV penetrates further into the body than infrared radiation does. And this is dangerous because these photons can collide with and damage the DNA in our cells, which can sometimes lead to dangerous cancers. Did you realize that that's how some cancers occur? Skin cancer is quite common in our country, and it's all because we have a very intense UV radiation from the sun here in South Africa. So now that we've done some questions, hopefully you're getting a better understanding of the relationship between frequency and energy of electromagnetic radiation. But that's enough for now, so let's take a short break, and I'll see you soon. Welcome back from that short ad break. Let's continue with our unpacking of this concept of energy and how it relates to photons and electromagnetic radiation. Let's jump to our concept map to just remind ourselves of what we've said already. So we've been talking about electromagnetic radiation. Whoops, wrong slide. Need to get my pen activated. We've been looking at electromagnetic radiation, and we've unpacked how it behaves like a wave and a particle. We've discussed how it propagates from one place to another. We've linked this idea of a spectrum of electromagnetic radiation to each type of electromagnetic radiation having its own different frequencies. And now, most recently, we've looked at how the frequencies can be related to this concept of energy using the formula E equals hf. Now, before we go further, let's do some practice to make sure that we've understood these ideas and see how they can be used to better understand things that happen to us around electromagnetic radiation on the day-to-day. So this question asks us to explain why a doctor always needs to wear a protective vest when performing an X-ray on a patient. You can see in the photograph down here, doctor, or in this case a vet, wearing a X-ray protecting vest. It's usually got some heavy, dense material like lead in it to prevent the X-rays from getting into them. But we want to understand why they need to wear this protective vest, but you don't need any protection when you use your cell phone. Now, cell phones are a staple of modern life. We see them everywhere we go, and we know very few people who don't use them, at least in part. But a lot of people say that they can be dangerous. They use electromagnetic radiation to transfer signals. So can we use what we know about electromagnetic radiation and its energy to see whether it really is that dangerous to use a cell phone? Let's have a look. So we're being asked to explain why a doctor needs to wear a protective vest when performing an X-ray. Medical X-rays have a wavelength of 10 times 10 to the minus 12 meters. So a very short wavelength, and therefore we know a very high frequency. While on the other hand, commercial microwaves that are used by cellular phones only have a wavelength of 5 decimeters, which is quite a bit bigger than the wavelength of the X-rays. So let's use those values for each of these types of electromagnetic radiation to see how much energy a photon of them would transfer. To do this, we're going to make use of a different version of our original formula for energy, wherein the frequency has been replaced with the speed of light c divided by the wavelength. We obviously got that from our wave equation from the previous lessons. So to find this answer, we're going to need Planck's constant, h, which we've written down, the speed of light, 3 times 10 to the power of 8 meters per second, and then we're going to have to substitute those values along with our wavelength for medical X-rays into the formula to get the answer. To do that, we'd best use a calculator. So our formula is E is equal to hc divided by lambda. So we're going to need a fraction, and into our first bracket we're going to put Planck's constant, 6.63 times 10 to the minus 34, close bracket. And we're going to multiply it by the speed of light, which is 3 times 10 to the power of 8, whoops, I've added too many, times 10 to the power of 8, close brackets. And this all needs to be divided by 10 times 10 to the minus 12 meters, the wavelength. Once we have that, we can push equals, and we get that the energy value is only 1.989 times 10 to the minus 14. 1.989 times 10 to the power of minus 14 joules. Quite a small amount of energy from a single photon of a medical X-ray, hey? But how does this compare to the energy of a cell phone? Let's have a look. So we're still being asked to find the energy here, and we're going to use the same formula as before, but now the wavelength is different because we're examining those of commercial microwaves. They have a wavelength of only 5 decimeters. Now, when we see this decimeter value, we must remember that we're going to need to convert this value into meters. All right? 1 decimeter is 10 centimeters, so 5 decimeters is going to be 0.5 meters. Still quite a large wavelength. So now that we have our numbers, we can start to do a calculation, can't we? Let's go. We're using the same formula again because we do not have the frequency of the cell phone electromagnetic radiation for this particular question. Again, we only have its wavelength. So, just as before, we need to make use of our calculator. Clear the last sum, but the formula is still the same. Need our fraction with Planck's constant, 6.63 times 10 to the minus 34. Once again, multiplied by the speed of light, 3 times 10 to the power of 8. But now, the value is only divided by half a meter. And when we push equals, we can see that our energy reading is 3.978 times 10 to the 25. 3.978 times 10 to the power of minus 25 joules. So would you look at that? The amount of energy a photon of cell phone radiation is carrying is significantly smaller than that of a medical X-ray. So what can we infer from that information? All right, so we have already established that medical X-ray photons have an energy of 1.98 times 10 to the minus 22 joules. And we've just calculated to show that the photons of commercial microwaves, those used by cellular phones, have an energy of only 3.978 times 10 to the minus 25 joules. Once again, an order of more than 1,000 less than those of the X-rays. So it's obvious to us right now that X-ray photons carry a lot more energy and so are able to transfer more energy to the materials that they impact. While in the case of cell phones, the energy is quite low and therefore is not really able to allow the photon to penetrate very deeply into you or me or anything around the cell phone. Let's have a further look though. We can clearly see that medical X-rays have a much higher energy output than commercial microwaves from cellular phones. The photons of commercial microwaves had significantly less energy than even the infrared photons from the fire in the question that we calculated in the previous segment. So, do you still think that cell phones are dangerous, even after we've done all the calculations? Hopefully next time you hear someone tell you that cell phones can cause cancer, that you'll have the information now to tell them they have absolutely no idea what they're talking about. Let's look at another question quickly, this time from an exam, to see what you might be expected to produce. So our question simply says, consider a laser pointer and a cell phone, as shown in the images below. This is a typical laser pointer like used by professors and kids as toys. It just shines a dead straight line from the pointer. And a cell phone we are well versed in. Our first question says, state the type of electromagnetic radiation that is emitted by the laser pointer and the cell phone. So have you used the laser pointer before? I'm sure you've at least seen a cell phone in use before. So which one do you what type of radiation are they each using? Let's have a look. Laser pointers emit red light, which lies in the visible spectrum. And so we know well that red light has a wavelength of 620 nanometers. Our next question of this longer question asks us to define the term photon. Do you remember what a photon is from the previous segments? Can you remember its definition? Remember that you need to know all these definitions as part of your preparation for tests and exams. So let's see what the definition is. A photon is defined simply as a quantum of energy and that is associated with electromagnetic radiation or energy. Remember, a quantum is just a fancy word for a packet of energy that can't get any smaller. So the definition makes a lot of sense that photons are just packets of energy associated with electromagnetic radiation. Let's go further. Part C of this question says, if the laser pointer uses light of wavelength 620 nanometers, we are told that we need to calculate the energy of a single photon of this red light. So how are we going to do it? Just like we've done it in the past, we're going to use our formula E is equal to hc divided by lambda, where h is Planck's constant and c is the speed of light. Let's move straight to the calculation. So in our calculation, we need to substitute our values. But one thing we must make note of is that the wavelength is not in meters and needs to be converted to 620 times 10 to the power of minus 9 meters because it's nanometers. So to do our calculation, we're going to need our calculator. Quickly clear it. Our formula is still the same. We have in brackets 6.63 times 10 to the minus 34 for Planck's constant, multiplied by the speed of light, 3 times 10 to the power of 8, all divided by our new wavelength for red photons, 620 times 10 to the minus 9 meters. Oh, I've made a mistake on the calculator. Let me just fix it. And then we hit equals. And we get that the energy of a photon of red light is only 3.208 times 10 to the power of minus 19. So we can see that the light from a red laser pointer carries quite a small amount of energy. What else does this question ask us to explain or understand? The last part of this question, part D, simply asks us to use our understanding of electromagnetic radiation to explain why it is very dangerous to shine a laser pointer into a person's eye. Now, from our previous calculation, we had shown that there is some energy associated with the photons from the laser pointer. Now, what makes this particularly dangerous is not just that they're going to transfer energy to someone's eye, but also that a laser pointer produces a very narrow beam of light that is full of many, many photons, and so can easily damage the sensitive tissue at the back of someone's eye. So remember, don't ever point a laser pointer at anyone's eyes. Right, that's all we have time for. I hope you've enjoyed all of this unpacking of the concept of energy and electromagnetic radiation.